So, since rc4 and most famously WEP is beaten to death, we will still keep on bashing it. So, without further ado, Martin.
Thank you. So thank you to be here, because it's a talk about cryptography, but to be honest, there is practically no math. So it should be intuitive, and you should be able to understand this, I hope. So I will present you a joint work with Pouyan Sheperdad and Serge Vaudenet. This work is about new attacks on rc4, and which can be applied to WEP. This topic is about cryptanalysis, and sorry, I don't know, but if you remember the buffer overflows in the 90s, it was very hard to understand how to find them. You had people, okay, I'm smart, I know I found this one, I'm very smart, I found this one. How did you do that? I don't care, I'm just smart, and so on. So it's like this in cryptanalysis. People break cipher and they just don't say how. They just say, I broke it, I'm just the best guys, whatever. So it's not my case, so I need to work. And that's why I try to find how to find weaknesses in crypto systems. So the idea is just like fuzzers who can find automatically buffer overflows. It could be interesting to have automated cryptanalysis tools to find weaknesses. So the goal here is more to show you how to find cryptographic weaknesses than just to present this flaw. So just check if it works. Yes. So the first part of the talk, I will just present you WEP, not all the stuff, all the mathematical stuff. As I said, the idea is to have an intuitive description, to understand why they did it wrong. Then I will speak about rc4. So there we have to understand how it works, but it's one of the easiest to understand crypto system. Finally, I will present you a part of rc4 called PRGA. So we will find new weaknesses in it. And the fourth step is, okay, it's white, but it's a black box. The idea is to see the cryptography as a black box. I don't care at all what's inside. I just want to find weaknesses. And finally, probably the most interesting is the implementation of the attacks to crack more easily web networks, wireless networks. So let's start with WEP. So WEP means wide equivalent privacy, which is not a good thing, because if you read it, it doesn't say very strong, secure algorithm or whatever. So it was defined in 1999 by the IEEE 802.1, and it used rc4 as a stream cipher. So rc4 is a stream cipher invented in 1987 by Ron Rivest, who is the R from RSA. And it has been disclosed publicly in 1994, and people try to break it because it's very simple. There is only 2 times 4 lines of code. And it's still the most used stream cipher by SSL Communication, WPA, Microsoft, Oracle, or whatever. So basically how rc4 works, you have to know a secret key, and rc4 generates some random bytes called key stream. And when you want to encrypt something, you just do an XOR with plain text, and you obtain the cipher text. So it's what we call a stream cipher in cryptography. The problem with WEP, that is a wireless communication, and then you can lose some packet. So for example, if you have a sender who generates enough key stream to encrypt 4 packets, so he has 4 plain text messages, then he encrypts them by using the XOR operation, and he starts to send them to the receiver. The first one, the second one, and the third one is lost, and the last one is sent. So now the receiver receives 3 packets, ciphertext 1, 2, and 4. Thanks to the shared key, it can generate exactly the same key stream, so it just XOR them to recover the plain text. And as you can see, at ciphertext 4, it starts to recover nothing, so the communication is broken. So that's a big problem to use RC4 in wireless communication. So WEP used a solution, it's to encrypt each packet independently. So it's probably not the best, but they choose to do that. So in practice, you have always a secret key. You generate one key stream, which is the same for the same secret key. So let's say it's key stream 1. You XOR with the first packet, and you obtain ciphertext 1. Now for the second packet, you use the same key, so you will generate exactly the same key stream 1 again, XOR with another text. Let's say the second packet has another payload. Then you obtain a second ciphertext. But we know that with the stream cipher, you should never use twice the same key stream. So why? Because imagine that a sender does the same, so he has 2 times the same key stream. He encrypts 2 plain text packets. He sends them to a receiver. If there is an attacker who can listen to the traffic, he can simply XOR both ciphertexts, and it will cancel the key stream, and then he has the XOR of 2 plain text. It may be hard to exploit, but you can do it easily, in fact. So WEP, to avoid this risk, decided to add a counter to the fixed key. The idea is quite simple. You have always the secret key, which is now called a fixed key, and you just add a counter, let's say 3 bytes. So for the first packet, you use a counter equals to 000, then you obtain a specific key stream bytes. For a second one, you just add +1 to the counter, and then you obtain another key stream, and for and so on for all the packets. So basically now, the secret key is first composed of 3 bytes called the counter or the IV, and then you have the secret key, the real secret key, which is fixed. Of course, the receiver has to know the IV, otherwise he cannot generate the key stream. So what he's doing in WEP, you have a header, and then you put the IV, the counter, in clear. So the receiver can read them and generate the correct key stream. Okay, that's it for WEP, so just what we have to know. Now let's have a look to RC4. So as I said, RC4 is a stream cipher. You put secret key, and then you have the key stream. So now let's look inside RC4. In fact, you have 2 algorithms, KSA and PRGA. KSA stands for key scheduling algorithm. So basically, key scheduling is permitting stuff according to the key. And PRGA is a pseudo-random generator algorithm. I will show you how they are used. So first, the secret key is the input of the KSA. And the KSA generates an array of 256 bytes called S prime. This table is a permutation of value according to the secret key. And then, when you need 1 byte of the key stream to encrypt 1 byte of the plain text, you use the PRGA, which will generate the key stream bytes. So let's have a look to the KSA. Okay, the only slides with math, but it's trivial. There you have the algorithm of the KSA, so you may understand why RC4 is so popular, because people think that it's easy to analyze it. What we do first, there is a loop to define the array S. S of I is equal to I. It means that S of 0 is equal to 0, S of 1 is equal to 1, up to S of 255 is equal to 255. Then you use 2 registers, I and J. And you will see that J first is equal to 0, and J is equal to, let's say, 7, which is defined by the first byte of the secret key. So the first byte of your secret key defines the value of J. Let's say it's 7. Then what you do is you swap these values pointed by I and J. So instead of 0, 1, 2, 3, you have 7, 1, 2, 3, and at 7 you have a 0 now. Then I is incremented by 1. So it's pointing here. And j the value of j is according to the previous value of j and the second byte of the key stream. Let's say it's 12. Then you swap the values. And you go on. I is equal to 2. J is equal to, I don't know, 123. So you swap these values. I is equals to 3. J is equal to 201. So you switch them. And 4 is equal to, yes, j is equal to 12, so you switch them again. So it's what you are doing for all the 256 values. So what's important is to see how is working I. I is incremented by 1 from 0 to 255. So basically what's happening to I is always pointing a value on the right. So it means that this value will never be pointed again by I, because I is always moving like that. So that's a weakness, in fact. On the other side, j is quite random, not totally random because dependent on the key and some values, but let's say it's random. So it means that on the array, j is just moving randomly. So what you can say is that sometimes a is on 10, it will go there, and there is a probability that j will not point any value before 10. And this probability is not negligible. In fact, in 1995, Roos found that according to this bias, you can determine some value of S prime and the secret key. That's the math part. So what it say? Sn minus 1, which is S prime, this is the same. So the table generated by the KSA, some value of them are correlated to the secret key. So for instance, the first value, so S prime of 0, is equal to key 0 with a probability equals to 0.37, which is not correct, which is a strong bias. Normally it's 1 over 256. So what we have to remember is from S prime, if you know some value of S prime, then according to a certain probability, you can recover some byte of the secret key. So in cryptography, we call it an inversion. So you can invert case A. But in fact, S prime, you can't know exactly what are the value of S prime, because S prime is internal to rc4. You don't have access to it. So that's why the second idea is to find weaknesses on the PRGA. So how is working the PRGA? It's quite similar to rc4. It just takes the S prime table that you can see here, 18, 3, 212, 11. And then you have to register I and J. Let's say at the beginning, I is equal to 1. So then you say J is equal to S of 1, which is 3. So J is equal to 3. Then what you do is you're just swapping both values. So you're modifying a little bit the table. And then to obtain the first key stream byte, you just take S of I plus J, so 7 plus 3, which is 10. And then you take the value at S of 10, which is 189. So that's what you are doing to have one key stream byte. The interesting thing is that for each byte generated, we slightly modify the table because 2 values are swapped, but only 2 values, so it's not a lot of. So maybe with only this modification, we can find PRGA weaknesses which can recover S prime from the key stream. And some people found them. So this is a quick overview of them. So the first one is Roos and Wagner, who found them in 1995. I call it conditional attacks because it's not an unconditional attack. You have to know exact values. So it's not covered in this part of this slide, so I just put them like this. The first real bias of PRGA was found in 1996 by Bob Jenkins. He published on his website these two biases. So what he says, the first byte, the byte I of the key stream is equal to I minus S of prime of J, with a probability equal to 2 over 256 instead of 1 over 256. And if I have no solution for that, okay, I don't know, it's not useful, I can't explore them, but I found them. He found another one. It was in 1996. There you have the famous Führer-Montan-Shamir attack, FMS, which is again a conditional attack, which is in fact mostly the Roos and Wagner attack found in 1995. And then you have another bias of the PRGA found by Montan and Shamir in 2001 at FSC, Fast Software Encryption. And then what they found is that the second byte of the key stream is 0 with a probability about 2 over n instead of 1 over n. Consider n as 256. Okay, David Hulton found additional conditional attacks, such as Andrea Bito, and probably you know Corec, which are mostly implemented in aircrack. The Klein attack is another bias, is the exploitation of two biases from the KSA, which is a Roos attack, and the bias of Jenkins in the PRGA. So what did Klein? He put two biases together and started a key recovery attack. Another PRGA base found by Paul Ratti and Metra in 2008. Okay, it's quite complicated, but basically, okay, forget about this one. It's not interesting, but basically we have three biases on the PRGA, and then I will present you some new one. So as I say, the idea, written here, is to bind KSA vulnerabilities to PRGA vulnerabilities to obtain from key stream the secret key. There you have the key stream. You recover with a probability S prime. Then with the value of S prime, you recover the secret key. So that's the goal of the attack. If we look at successful attack, first I said FMS. So it's basically the Roos for KSA and the Roos and Wagner and Führer, Montan, Shamir for the PRGA. And this is the first practical attack on WEP, FMS. Then you have another one. As I said, the Klein attack, which is the exploitation of the Jenkins bias on PRGA and the Roos on the KSA. Another one, not still exploited yet for WEP, but it's a Metra and Paul attack, which directly correlates to the Roos weaknesses on the KSA. So we can conclude, okay, for the KSA, we have basically one attack, it's a Roos correlation. But for the PRGA, we have at least 3 attacks, so why not try to find new one? And that could be useful to break rc4 and WEP. So let's say now how to find weaknesses on the PRGA. Okay, so you know exactly what you have to do now. But how? Because as I said, in cryptography, they don't give you method. They just say, okay, if you're smart, you will find it. Otherwise, just do another job, I don't know. You're not a math guy. Or... So I'm not a math guy, so I will use computer to do the work for me, right? So why not to do an automated discovery of bias? And okay, let's call it automated cryptanalysis, but what to do? Okay, take an example of the fuzzers. What they do what everybody do when they don't know what to do, an exhaustive search. So why not try all the possibilities to find if there is a bias or not. And to know if you are successful, you just have to rediscover all known PRGA biases. And at least maybe you can find new one. So first to do is to take all the value inside a round of the PRGA. By round, I mean when you generate the first byte of the key stream, it's the round 1. When we generate the second byte of the key stream, let's call it round 2. So inside a single round, you have these values: I, J, S of I, S of J, and Z, which is the value of the key stream generated. So basically, when you don't know what to do, you say, okay, let's try to find linear correlation between them. So we'll just put them here. I, J, S of J, Z equals to a constant. And then I put coefficient and say, okay, let's try all these equations. And I will look at every time this equation is correct. If it's over, the probability to be correct is 1 over n, 1 over 256, there is no bias. If it's more or less, there are biases. So the complexity for that, considering that for A you have all the value from 0 to 255, it's too big. But you can quickly put the I on the other side, because you can consider I as a fixed value, and then you have reduced to one parameter the equation. But the complexity is still too big, so the other things to do is, okay, all the coefficients for the previous attacks, for the known attack, use -1, 0, or +1 for the coefficient. So why not just be limited to this coefficient as well? At least we will recover all the known attack. When you have this, you don't know what to do. When you don't know what to do, you do a picture. And then here, you have all the equations according to the amount of time the equation is correct and the value, the constant value C. And what you see here, it's not completely flat, so there is interesting things. There is biases for all the C's decreasing, there is peaks here. So that's interesting. This is only for round 2. And then you spend 2 months with a book and pen, and you write all the table with all the attacks you have found. So first of all, you see that the Jenkins biases are here. You can see that according to the coefficient for J, S of I, Zi, you have exactly the Jenkins equation. And you see you have new ones. So it's called new 0, new 1, new 2. There you have new biases where Z is not involved. Basically, you have the coefficient for Z which is equals to 0. So maybe it's not easy to exploit them, but at least they exist. And if you look at U1 and U2, there is dots, dots, dots. So why? Because they are strange. So why? Just look at this equation. Let's try to do a picture. Okay, the bias, which is normally equals to this value when it's not, there is no bias, is very strong for the wet one, which is round 1, and it decreases. It decreases, and around 256, it's not even exploitable. So again, okay, I don't really understand, so let's do this in 3D. And there you can see that, okay, all the green part, green-blue part, is not really exploitable, but there you can exploit it for round 0 to, let's say, at least 48. And when C is close to 0, you can exploit it negatively, because the bias is negative here, and the bias is positive here. So it gives you a lot of new bias. Before that, you had only Jenkins bias, then you have a lot of new bias. For new 0, it's the same thing. New 2. There you can see that the probability of the success of the bias is, the bias is not as strong as before, and it's strange. So let's see in 3D. And there you can see, okay, there is sort of mountain here and valley here and here, so I can exploit when it's red and blue. Okay, I will take all the equations, because the goal is to have as much equation as you can. So the bias are for every round, but we saw that for specific rounds, for example, for the first byte of the keystream, so round 1, you have additional equations, and then you recover the equation from Paul, Ratti, and Metra, so the equation already known before that. So okay, that's good. At least we found new equation, and we have all the known equations. Then for round 2, we have additional bias. For instance, you have the Montin and Shamir bias there. And you have new 4, new 5, new 6. New 5 and new 6 is strange, because when C is even or odd, it's different. So you can see the graphs here. I have no idea why, but at least what I want to do is just to exploit them. And we found additional correlation for round 16, especially new 8 and new 9. Which are not strong, but at least they can be exploited. So when I say round 16, in fact, it's round 0 modulo 16. So it's round 16, 32, and so on. Okay, now, we have a lot of too much biases. So how to exploit them? So we think about this. No, I don't have to say think. We asked to a guy who is good at math to think about it. And he said that when S of J is involved, you can use the KSA-Roos correlation. Okay. So for instance, there is 2 examples here. New 008 can be bind to Roos correlation. So it's a new attack you can use. It's working. And new 009 with Roos again. And it gives you new attacks to improve the key recovery process. But now you spoke with a mathematician and said, okay, it's quite lame to just use the coefficients. It's not professional. So he says some strange things about Fourier transform and spectral approach. So it's another method. It's quite simple, but I will not explain it here. So the main idea is to avoid to be limited to -1, 0, and +1. On the other side, you can limit all the attacks to bias where Sj is involved. So you're sure you can use them with the Roos correlation. So you let the computer do the work, and then you find all these new biases. And these biases can be used as well in practice because, as I said, S of j is involved. You can see here, there is a coefficient, but those are not involved, so you're sure you can use the Roos correlation. As you can see, the values are not just -1, +1, and 0. So you cover the whole potential linear correlation on PRGA. Okay, so it's good. So why not just be more simple? It was a black box, but we don't see it. So why not consider RC4 just as a black box directly and don't care about how it's working inside? We have a key stream, and then what we want is from the key stream, we want to recover the secret key. So why not just use a linear equation with all the key stream bytes from the first to the 256 bytes, and all the key bytes, key 0, key 1, and so on until key L-1. Okay, so we try to do this, so the complexity is so big that you cannot really use it, but we saw that it was useless to look at the byte more than ZL, because it's like that, we didn't find a bias. So we reduced the complexity to the first L byte of the secret key and the first L byte of the key stream. So at the beginning, we say, let's say L is equal to 5, and then we hope to find something interesting. And we found all these biases here. So as you can see, there is what we call the Klein improved, so say the Klein bias, the Matra and Paul, Manta and Shamir, and so on and so on, and then you have new. So with this technique, just considering RC4 as like black box, you can find new correlation between the key stream and the secret key. And we did it only for L equal to 5, but we saw that all these biases exists with L equal to 16 bytes. L is the size of the key, so basically in WEP, most of the time the size of the key is 16 bytes. So the question is, okay, but before that we did all the research on PRGA, we found a lot of biases, and then with this method we found new biases. So what's the problem? What was wrong before that? So the main mistake is before that we tried to find correlation inside a single round of the PRGA. And with this technique, we can find cross correlation between different rounds of the PRGA. And that the new biases come from this. And maybe, I don't know, but maybe we are exploiting another unknown correlation on the key assay. So that's why we found these biases. Okay, but who cares? At the end, we have found at least all known correlation and new ones. So this trivial, extremely trivial linear analysis of the elements of RC4, which is a cipher, the most used cipher, with it you can find a lot of new vulnerabilities. So even if it's very trivial, automated cryptanalysis seems quite efficient. Okay, now it's time to implement them. He's here. Okay, when you want to implement the attack, you have to improve them. So basically, you use rcrack. So the first programmer, the first developer of rcrack, Christophe Devine, is here, so you can. And rcrack use at the beginning was using only conditional attack from correct, and then he was using the Klein attack improved by Fiskin, Chu, and Weinmann. So you have Eric Chu here, so you can congratulate. And with these techniques, I will show them this technique. So, okay, so that's for me, sorry for that. But the attacks discovered by this guy were discovered independently by us, but nobody cares. And even worse, they were implemented much more better than us in 2009 because they did mistakes. So basically what the improvement of the attacks, the first idea is not to recover every byte of the key independently. Not independently, but try to recover every byte of the key in a row. So first you have to recover the first byte of the secret key, then you have to recover the second one, and so on. The goal here is to recover the sum of the key byte. So this is an equation, but what you have to understand, this equation is used to recover the pth byte of the secret key k. So as you can see here, you need all the previous byte of the secret key to compute this. And for this as well, you need to have the previous byte of the secret key. So the idea is very simple. It's just to put this equation on the other side. And then you recover the key sum, the sum of the secret key bytes. You have to reduce the probability of success, because in the equation you had some things where the previous byte were involved. And then you have an attack to recover the sum of the secret key byte independently. The problem is the probability of success decreases according to the byte you want to recover. So you can say, okay, it's useless because I just need to recover the 16th first byte of the secret key. But in fact, the key is repeated, so it could be interesting to attack the repetition as well. So at least until 47, you can still use this improvement. Another improvement we did is just to exploit the repetition of the IV, because as you remember, the IV is a part of the key which isn't clear. So if you know it, you can use it to recover the previous byte which is unknown. In this case, it's the last byte of the secret key, the last sum of the secret key bytes. After that, you can as well exploit the repetition of the key, as I said, so it's another improvement. Then you can do something not well detailed, so I hope to explain it a little bit intuitively at least, is with this technique you are recovering the sum of the secret key, but with the previous technique you were recovering byte per byte. So the idea is to merge both attacks together to improve the global recovery process. So to explain this, you have to look at the code, maybe it's more simple. And of course, all this improvement can be applied to the known key recovery attack, so correct attack, FMS attack, and the Klein attack, and so on. So even the new, in fact. So you can easily apply this improvement to the unconditional attack, so such as Klein, Paul Metra, and the new one you saw here, and the conditional attack, which are probably most known. Okay, now to evaluate the efficiency of the algorithm, at least for WEP, you just count the number of packets you need to recover the secret key with a probability of 1/2. Yeah, the first guy decided to do that like that, so to compare the results, everybody did the same. So with all this improvement, now we only need 9.8 encrypted packets to recover the secret key, a secret key of 104 bits. So I don't know if it may be interesting for you, but in fact the goal is to attack WPA, because all these attacks can be applied to WPA, TKI, IP. But the problem is WPA changed the key for every packet, so the goal is to go up until one encrypted packet, and then we could be able to crack WPA. It should be done, but it's not. So this attack are currently implemented for aircrack, NG. And yeah, that's it. And what what we can say to conclude is now we have the best key recovery attack on WAP, so we improve it, even if people say it's like beating a dead horse. As I said, these attacks are on rc4, but they can be applied to web, and cracking rep is the most used cryptographic attack in the world. So it's still at least fun, I don't know. So we found 48 new biases on rc4 using, as I said, an extremely trivial function of automated cryptanalysis. So it means that I'm sure you can find better things and go on with it. So mathematician, cryptographer are not the monopoly on the cryptanalysis. You can use tools to do that. As I said, the main goal is to break WPA TKI IP. So in cryptography, we said we have a theoretical attack, which means it's not available in practice, but it's a theoretical. So it's what we have, but not very interesting. And as I said again, maybe the interesting point is to understand how to find them. As you have seen, it's quite simple. You just have to understand the problem and to ask the correct questions, and then there is no fancy math or something incredible. It's just addition and linear resolution systems. So I hope I worked on the buffer overflow detection, and I hope to have such tools like advanced further for cryptanalysis soon. And that's it. So if you have questions.
So are there any questions? Oh, from the RAC?
There's one question in the RC. Are there any estimates for how efficient the use of the new biases is for a simpler distinguisher, e.g. the PRGA is used as PRNG?
Yes, so shall I have to repeat the question, or with the micro is okay? Okay.
Fine.
Oh yeah, but yeah. Yes, a distinguisher is when you don't have a practical attack on a crypto system. What you do is at least to distinguish the key stream from random values. So these attacks, because you can a little bit break rc4, you can use them as a distinguisher. So I don't have them in my head, but they are surely in the paper. And then you have the distinguisher. So it's the best distinguisher for rc4 as well. So when you have the best attack, you have the best distinguisher. So.
My question would be, what approach did you use to combine all these correlations to a single attack tool?
Yeah.
Because you can easily run into problems there, and usually you don't immediately know if you have taken a very good approach, or you can still improve your approach.
Yeah, so this is a very good question, because you have a lot of attacks and they are working differently. Some of them are very stable and others are completely wrong, and suddenly they are very, very good. So for that, you have to give weight to these attacks. So the first analysis, what we did, and probably the mistake on the attacks, is to take the math and to look at the probability of the attack to be successful. And then, let's say it's working to 0.3% of the K. So let's say the coefficient is 0.3% for this specific attack. But in fact, as I say, this attack is not working for a lot of time, and then suddenly it's working at 60%. So the average, the mean is something like 0.3, but in fact it's not. So in fact, the experiment, it's strange, because we were running the things, and so at the end, okay, this one is working like this, so I know that I will put the coefficient like that, and so on. So what I have to say, there is, for the computation, we use the probabilities, because you have to reproduce the same results. But in practice, you can largely improve these attacks by considering not a stable attack working always with the same probability, but changing from the time to time. So for our air crack, in this case, it's manually, the coefficients are, yes, subjective.
My question is just, you were saying that For VPA, TKIP, you need one packet. I mean, you would need to make this attack work on one packet. Now, the problem with this attack is that this is a statistical attack, right? So one will not give you any kind of statistical distribution. Half working. Okay, so basically you need more than one packet to have any kind of statistical means to analyze it. So how could this, I mean, my head is not computing this equation properly. How could this work on one packet?
Yeah, for WP it's quite complicated because even if you recognize one per packet key, you can do nothing with it. You can at least just read the content of the packet. But if you look at the distribution of the key on WPA, I'm sorry, it's getting more cryptographic stuff, but you have a temporal key, and the temporal key is used for at least 2 to the 16 packets. And when you have additional, it's a Moan attack published in 2004, I think, where imagine that you have recovered part of the per packet key, you can recover the temporal key. So the idea of these attacks is even if you don't find correctly the correct key, then it's a statistical attack, so you will recover some byte of this key and this key and this key and this key, and thanks to the statistics, it will give you the correct temporal key. And with the temporal key, you are able to inject data, and at least for 2 to the 16 packets, but you can inject and you can read the content of the data. So the attack is more complicated than just recover the per packet key. What I wanted to say that you can apply them, at least they are working for WPA, but in practice you cannot exploit them.
So, any more questions? No? So thank you, and please create stacks of 7 shares. Thank you.